Fantastic. Welcome everybody to day 2 of this webinar series. Thank you so much for joining us again today. Thank you to those who completed the survey or the quiz yesterday. We had a great response, and so far everybody has passed. So well done. Give yourselves a round of applause. You're doing great. And I hope you enjoyed our chat responses. We gave some attention to each of the questions that came up, and hopefully that you'll be able to get the answers that you need just by reading that email. If you're still struggling a little bit, feel free to let us know. And of course, if any questions come up from today, please pop them in the chat and we'll respond in the same way this afternoon. I'm going to hand straight over to my dear colleague, Gemma Turon from Ersilia Open Source Initiative. Gemma, take it away. Thanks so much.
Thanks, Nicola. Hello, everybody. Good morning or good afternoon, depending on where you are at. So, welcome to day 2 of this online course. Great that you make it through to day 2. Hopefully, you will stay with us for the entire course. Just before we get started right away, some key reminders. You will find all the course contents, all the links, including the recording links once they are updated. In this, here it is a bit.ly, this is a short link, AI2050 online. Okay, so if you go there, you will be able to download the slides, you will be able to go to the recorded presentations from yesterday, and it's also where you will find the links to successfully complete the exercises. Every day, we follow the same structure. So we are giving a presentation that is roughly about 50 minutes. Feel free to drop your questions in the chat. If we have time, we'll tackle them during the live session. If we don't, as you have seen, we will send some answers through at the end of the day, so that you do get your questions answered. This is done this way because, of course, of time constraints and the number of participants. Then we really try for you to get some hands-on exercise, some kind of a small activity. We allocate roughly 20 minutes to that, and you are supposed to submit your results through the links provided. Again, you can follow the links on the AI2050 online platform. If you don't manage to submit before we get back together because you're struggling with internet or because you may be more newer than others to data science and drug discovery, it is not a problem. You still have the entire day to go through the exercise, to think it through, and to finally submit your results. After that, we'll get together again for roughly 20 more minutes, and we'll go over the exercise, how it looks like, what are the key points you should have paid attention to, and then if we have time, do a short question and answer, okay? So this is the same structure for most of the days. At the end of the session, you should be saving up 10 extra minutes so you can answer the evaluation form. As Nicola has just said, these evaluation forms are important for us. First, to see if everyone's more or less following the content so that we can adapt for the next days. And also, very importantly, to see if you are actually in the course and therefore eligible to receive a certificate at the end of it, right? So to receive this certificate, you must attend all the sessions and you must answer all the evaluation forms. The course is iterative. We build upon each previous session, so we really encourage you to come on time and stay throughout the entire session of the day, do the exercises on the same day, the evaluation form, so that you're ready for the next day to build upon this knowledge. And yeah, that's it, right? So welcome, thanks for being here, and I hope you find today's session as useful as yesterday. So today's goals are to learn more about machine learning models that are relevant to drug discovery and understand how we can easily apply those models that are already developed to our research. We'll give some overview about training models, but this is not the main focus of the course, as we already said yesterday, because that would require much longer training time and also much some previous knowledge on programming, basic AI knowledge, etc. So this is not the aim of this course. If you are already building your own ML models, that's great. Please stay on. You'll also learn some things that are useful for your research and for building more models. If you have never used or built AI, that's the right course for you. We are going to show you how to actually leverage models that are already built. Okay, so with that, from yesterday, Jason went over the basic classification of machine learning models that are pertaining to the drug discovery world. So first, we have unsupervised methods. Unsupervised methods are those that use unlabeled data. They are useful, for example, to cluster molecules into different groups. So to see if we have a specific chemical series in our group, natural products, synthetic compounds, whatever it is. We call them mostly, we do them in 2D projections. So we reduce each molecule to two numbers that are then easy to plot. So here, each dot will represent a molecule, as we saw yesterday. So it's very easy to visualize molecules in this kind of 2D projections. And for example, it allows us to do similarity searches, right? Because if two molecules in these plots are closer to each other, they are more related than two molecules that are separated from each other. Yesterday, we saw different methods and how each one has a slightly different interpretation of this kind of plots, but the base idea is this. Unsupervised methods are used on unlabeled data. In the context of drug discovery, they are very useful to cluster molecules and to see quickly if our molecules are similar or dissimilar between them. The second class that we went briefly over are supervised methods. Those use labeled data. In the context of drug discovery, mostly we mean a molecule and an associated activity. The activity is the label of this molecule. And what we want to do is either predict this activity, the exact number, that would be a continuous a regression model, or we simply want to classify if a molecule is active or inactive, right? A simple binary classification between 0 or 1. Remember that by convention, 0 is inactive and 1 is active. Active in whatever assay it is, okay? And then we have a third kind of models, which are called reinforcement models. Those are learning from the environment. For example, agentic AI, where you have a conversation with ChatGPT, but also all this realm of generative models that keep learning from the molecules they generate to generate better candidates. Yeah, that is the kind of reinforcement learning. We'll briefly see those on the last day of the course, on day 4, Thursday. Okay, so today we are focusing on this bit here on supervised learning. We'll see some concept from yesterday. We'll expand upon those, and we'll do a first activity that we will continue tomorrow. So let's start by the easiest, by the most obvious. We want to use supervised machine learning for bioactivity prediction, right? A very simple task. If you're an experimental biologist here, if you're a chemist also, maybe you have encountered this kind of setup where you have your different compounds and you put them in different concentrations, yeah, on a bacterial culture. In this case, for example, we said this is Acinetobacter baumannii. So, of course, what you want to see if the bacteria keeps growing or it doesn't grow. That can be very simply assayed by optical density, right? If the bacteria grow, they are darker, so there is, the light doesn't pass through. If the bacteria is not growing, the wells are lighter. So even by eye, you can already see whether a molecule is killing or not the bacteria. So you do this across several concentrations, and then you want to test which, what is the concentration that is killing the bacteria for each molecule. This typically is called an AI2050 assay, where you obtain the number, the micromolar, the concentration value at which you actually kill the bacteria. And I'm putting here made up, of course, examples. So in this case, we see how there is a lot of bacterial growth. So this molecule requires a lot of concentration to kill the bacteria, and this one obviously much less, and even less. This would also be less active, yeah, and this would be somewhat an active molecule, right? So this is what you obtain from an experimental setup. To make this easier to interpret, instead of using all the IC50 values, what you can say is, look, I am looking for molecules that I consider active at a certain cutoff. This is the first cutoff. There, we will talk a lot about cutoffs today. This is the first cutoff that we need to remember. We call this an experimental cutoff because it comes from the experiments and from our informed knowledge. It is not always the same. It depends on the stage of the drug discovery cascade that you are, on your particular case, if you're working with drug-resistant strains, if you are working with gram-negative or gram-positive bacteria. But let's say, as an example, that we want a cutoff of 10 micromolar. In this case, first molecule that has an IC50 of 50 would be inactive, but the second one would be active, inactive, and active, right? That's very obvious. I'm going slow because I want everyone to follow these basic concepts. Otherwise, along the presentation, we'll get lost. So basically, if we use to train a model this data, we are training a regressor. If we use this data, we are training a classifier. Pretty obvious, right? Great. So let's move on. Let's continue with this example of training a model for bioactivity prediction. Jason very briefly presented the steps yesterday to train a model and what we have to take into account. So we have our training set, which is associated to labeled data, yeah, with activities. We feature these molecules, meaning we convert them to vectors, and then we feed a machine learning model. So the model learns whether each of these representations is an active or an inactive. So when it encounters a new representation, it will be able to tell you whether it's an active or inactive. If we look at the first step, the featurization, and this is a very, very basic, simple representation, but I hope it's quite informative. Just by looking at this, you can see how first molecule and third molecule that are actives, yeah, this just graphical depiction of its featurizer is very similar. And the new molecule is also very similar, this featurization, right? So it will probably be predicted to be an active by the model. That's as simple as it can get, okay? So really at the end of the day, what we are measuring, what we are trying to infer from our knowledge is whether a new molecule will be active or inactive. Now, this featurization step, therefore, becomes quite important, especially in the drug discovery world. So the first concept we need to remember, and probably if you read literature, you'll see this a lot, where you select features. I put here a very basic example where we want to use features that are discriminative of our actives and inactives. These features can be very complex, but they can also be very simple. In this case, I've chosen 4 features. This is an entirely made-up example that's not real, but I've chosen 4 things that we could look for: the number of rings the molecule has, the solubility, the number of fluors, and its molecular weight. These are all numbers, so these are all descriptors of this molecule, right? So then we want to see which of these descriptors is actually allowing us to separate our actives and inactives better. In some cases, let me give here a few examples. Some descriptors are able to really do a very good separation between actives and inactives. These are good features. These are features that are going to be very informative for our model. And these are what we call interpretable features. Someone was asking yesterday about interpretability, so we can do this kind of studies to see for these features that are really easy to understand, like solubility or molecular weight, if they are predictive of active and inactive. For some other features, they are not informative or not obviously informative. They don't discriminate well between our actives and inactives. We may discard them for further model training, okay? So I hope this is clear. We use first step, which is called featurization, and we try to use features that are helping us separate between actives and inactives. We can do feature selection, looking feature by feature, or we can also use a more, let's say, big data approach, which is something that we do quite often at Ersilia. And the idea of using this big data approach is to use several fingerprints, not only one, but different types of fingerprints, of descriptors, of featurizers. Jason already introduced this yesterday. So we have some very basic classical chemical fingerprints from where a molecule, we basically look at its chemical structure and we represent it, right? So in this case, for example, what we can do here is build a vector that is just zeros and ones. And we put a 1 every time we encounter a particular chemical feature, like chlorure, fluor, etc., 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 right? So basically, this would be a very simple vector that is composed only of zeros and ones that is describing the chemical structure of the molecule. But by now, we know that this is not the only thing we can do. We can build much more complex descriptors. Yes, so we can simply have what we call 0D descriptors. So for example, the molecular weight. We can have these 1D descriptors that basically tell us something about the chemical structure, but a bit more complex 2D, and even 3 and 4D descriptors that tell us about the chemical structure of the molecule in the space. Some of you may be aware of, these become very relevant, especially when we are already looking for targets, for a particular target, a particular binding pocket, where the 4D structure of the molecule is very important for the binding. So these descriptors are what we call classical, that purely represent from more basic to more complex the chemical structure. But we also now have this, what we call data-driven descriptors. These data-driven descriptors are much more complex, are not interpretable, meaning that a human eye cannot just understand them the same way we can understand the molecular weight, right? Because they are built with deep learning. And what these descriptors do is they capture a lot of information that is not only related to the chemistry of the molecule, but is also related to its toxicity, to its side effects, to the network perturbation it causes, to the targets it interacts with. To build this type of descriptors, we require deep learning exercises. There is a lot of these descriptors that are out there that you can already use. You don't have to train them from zero. The same way classical descriptors are pre-built, these data-driven descriptors are also pre-built, and you can use them without having to build them from scratch, which requires a lot of deep knowledge. So what we do, and this is for those of you that are more advanced and maybe found this interesting, we are not going to dive deeper into this, but what we find very useful is basically from a single data set, we choose a collection of descriptors. We don't stick only to one. We choose some chemical basic descriptors like Morgan, Mordred, but also some more advanced descriptors like ChemGPT, which is based on natural language processing, the chemical checker, which is a very good representation of bioactivity, and so on and so forth. So we use a combination of descriptors to feature our molecules as best as possible, balancing computational performance and the number of descriptors that you have, because of course, every new descriptor is going to make your models bigger. But at the end of the day, what we are trying to do is to obtain good representations of these models, of these molecules, so that we can train a good model. For those of you that we are not going to go deeper into this today, just for you to know, if you are already building your own machine learning models and you want to expand the number of descriptors that you use, you can browse the Ersilia Model Hub. We'll see that in the next few slides. Please don't go away from the presentation. You can browse the Ersilia Model Hub and you will find a lot of descriptors ready to use. Okay, so we basically collect for each molecule an ensemble of these descriptors, numerical representations, vectors, and with that, we move to the second step, which is the fitting. In the fitting step, we can also use a kind of a similar approach where we don't restrict ourselves to a single machine learning method, but we try which ones are better. We may combine some of them. We may stay with only one of them to make a model lighter, but basically you need to do a bit of trial and error, try different architectures and see which one works better for your case. So in this model fitting, we have several categories. We have what we call classical machine learning models, which are tree-based classifiers. For example, I'm sure many of you know about XGBoost and random forest. There is auto machine learning solutions that help you determine the parameters automatically. This is also quite interesting. For example, FLAML. We can use MLPs, which are deep neural networks. For example, Keras, which also has an automated version with Keras Tuner. We can also use, instead of the entire set of descriptors, we can use dimensionality reductions, maybe not 2D, but 100D, for example. So we reduce all these large descriptors, which can reach up to thousands of numbers per each molecule, into smaller and more condensed vectors using, for example, what we saw yesterday, UMAPs, PCAs. And with those, we can train models that are lighter. And we can also use image-based descriptors, right? So remember that we can convert our molecules also into images, into bits, or the descriptors, we can arrange them into the image-like shape, and we can pass those to the models, So we can train CNNs and so on and so forth. Again, this is advanced. This is not the point of this course. We just put these concepts here for those of you that may be already at this stage in your research and want to learn more about how we do these things. I encourage you, if this is the case, to go through the publications, go through publications that we have in the Hub, publications that we have produced at Ersilia, and really learn more about all these different kinds of machine learning tools that are readily available for using out there. But what we want to focus on today, and let's go back, let's bring everyone back together. I hope we didn't lose anyone, is what can we do? We are assuming that the model is being trained by someone who has data and the knowledge to train a model, so that you can come with your molecule and basically obtain a prediction, right? This is great, but to do that, even if you're just using the model, you need to understand some basic concepts so that you will be able to assess whether your model is going to perform well, or this model is going to perform well or not for your particular chemical space. So let's dive into that. How do we know if the model that we are going to use is going to do well or not? What can we guess from the publications about the models that we may want to use in our research? So we need to learn the basics of model performance evaluation, so that when we read publications, we can quickly scroll for these items. We have a data set, or the people who train the models has a data set, which are the molecules and its activity. And we get what we call the train set, right? We went over this yesterday. So we have a train set. This train set is composed of we call it X, the molecules, and then our labels, Y, the activities, the Ys, active, inactive, inactives, etc. And we basically try to fit a model that is able to predict and to learn from whether each molecule is an active or an inactive. Once this model is fitted, we take the second chunk of our data set, a test set. Typically, this is 80-20 split, 70-30, 75-15, 75-25, sorry, that is the typical train test split. In our test, we have what we call the X test, so our test molecules. And for those, we predict a value. We predict activity or not non-active. And then we compare these predictions with our, what we call the Y real, the actual value, because remember that this is part of my original data set. Someone asked yesterday, And then we, of course, use this comparison of real versus predicted to measure how good our model is doing. Once all this exercise is done, typically a final model is trained on all the data. Yeah, so we get all the data and train a final model, because why would we want to discard data? We want to use all the knowledge we have, and we use this train test split as a surrogate of to see how good our models are. Okay, someone asked this. Not everyone does this final training, but typically that is what you will find. So let's go first to the classifiers. I want to stop here and see if there is any pressing question in the chat that we need to answer now, or we are good. Are we good? Sorry, maybe Jason or Nicola can.
Yeah, I think we're good for now. Just some questions around stereochemistry, or yeah, but we can address that, I think, at the end.
Yeah. Okay, great. Perfect. Let's continue then at the moment. So
Nicola has a hand.
Yeah.
No, ignore me. Keep going. We're doing great.
Okay. All right. So let's see how can we evaluate the performance of classifiers briefly, so that we understand the metrics that we will find out there in the publications. Everything will come together at the end of this session, and especially at the end of tomorrow's session. So hang in there. Okay, the output of a classification is a probability, and it's two numbers, okay? It's the probability of the input of my molecule belonging to category 0, what we call probability of 0, and the probability of my input belonging to category 1, probability of 1. By convention in drug discovery, 0 means inactive, 1 means active. And this remains true regardless of the endpoint. If it's bioactivity, probability of 0 means that the molecule is probability of being inactive, so not bioactive. So it's molecules that we do not want, right? We want molecules that have a high probability of 1 of being active. Whereas if we are talking about cytotoxicity, we want molecules that have a low probability of being active, of being toxic, okay? So just to understand the interpretation of these values. Obviously, probability of being 0 and probability of being 1 are complementary. They total to 1. So if you sum them, you will get a 1. So in these QSAR models that we mostly use in drug discovery, by convention, the probability of 1 is return, probability of active, yeah? And if we get this probability, then we have a, I don't know, 0.3, 0.7, 0.6. So maybe if what you want to get is whether the molecule is an active or an inactive, you need a second threshold, the second one. Remember that the first is the threshold that we use in our training data to say this is an active, this is an inactive, and it's determined by your experimental setup. It may be an IC50 value, a percentage of inhibition, optical density, whatever you are measuring in your assay, yeah? Here, we want to say, okay, I have a molecule with a probability of 0.1, and I want to say whether this is an active or an inactive. The threshold by convention, by default, will be 0.5 if nothing is specified. But you will see now in the examples that we are going to go through in this course, how this is actually not the case for most of the exercises. So let's look at this plot. This is the kind of evaluation I would do. This would be my test set for which I know the molecules that are negative and the molecules that are positive, right? Each dot represents one molecule. And here I have the score, the probability of 1 that my model, that my machine learning model has predicted for my data. So a priori, I like this a lot because I see that most of my true negative molecules have low scores, whereas most of my true positive molecules have high scores. This is great. So let's see, if we have a molecule that has a probability of 1 of 0.61, it will fall somewhat here in this graph. For the second molecule, which has a probability of 0.7, it will fall about here, 0.31, it will fall here, and 0.79 will fall here, right, in this graph. Now, these are unknowns, so I don't know whether they are true negatives or true positives. I need to define a threshold to say this is going to be a positive, this is going to be a negative. Because imagine that I am doing a prospective screening and then I want to test molecules. I may say I have all the resources in the world. I say anything above 0.5, I consider positive, and I'm going to screen everything in the laboratory. So if we put a threshold of 0.5, roughly around here, I'm going to say the first molecule is an active, the second molecule is an active, the third molecule, this one below here, it's inactive, it's below the threshold, and the fourth one is above the threshold. So again, it's an active molecule. If we use this default 0.5, in this case, if we look at the test data, we'll select most of our actives, we'll miss some of them, we'll misclassify some inactives as actives, okay? So it is not perfect, it's not bad either, right? So this threshold, in this particular case, by looking at our test data, it's okay. We can be more restrictive. We can say, I consider actives molecules that are above 0.7 only. So if they are above 0.7, the threshold would fall somewhere here. So the first molecule, this one, will be considered an inactive. The second one will barely make the threshold, an active. The third one, of course, will be inactive. And finally, here at the top, we will have an active molecule. In this case, with this more restrictive threshold, we will lose actives. Yeah, there is a lot of real actives that get lower scores. So probably in my new data, in my prospective data, is the same case. But almost no inactives will be misclassified. Where can this be interesting? For example, I am doing an assay where what I want is to be really, really, really sure of the actives that I get, because it's an expensive assay. I cannot test many molecules, so I want to test things that I know will be good. In that case, I want to be very restrictive with my threshold so that what I test is true. I don't care if I lose things. Then we can choose a very permissive threshold, in this case, 0.3. If we put a permissive threshold of 0.3, we will find these first molecules are active. So active, this one is also active. This one even is active, and also that one is active, right? So all these molecules that I've predicted, they will be predicted to be active. So we will get almost all the actives for sure in our data set, but we will also get quite a few inactives. Do we like this? Well, it depends. If you are in an initial screening, where what you want to have is a starting material, you want to screen molecules and find good starting material, you prefer to get maybe inactives in your screening, but as many actives as possible, so you don't lose any prospective candidates, right? So it's not good or bad. You need to decide for your use case whether you want to be more restrictive or less restrictive. If that is clear, we can then go to these confusion metrics that can be confusing indeed. So let's take this step by step. What is a confusion metrics? It's a way that we use on our test data, okay, to get some metrics of performance. So here I'm plotting real knowledge. I have molecules that I know are inactive and molecules that I know are active. Whereas in the x-axis, I have molecules that are predicted to be inactive or predicted to be active. Okay, if a molecule is predicted to be inactive and indeed it's inactive, I have a true negative, right? It's predicted to be negative and it's true that it's negative. If I have a predicted active and indeed it's active, I have a true positive. It's predicted to be positive and it's actually positive. But if a molecule is predicted to be active, but actually it was not active, I have a false positive. If the molecule is predicted to be inactive, but actually is active, I have a false negative. This is pretty obvious, right? So from all these numbers, we can derive metrics. To classify the molecules into true negative, true positive, false negative, we have had to set a cutoff, okay? A cutoff to decide whether my predicteds are active or inactive, what we just did in the previous slide. If you don't see any information, this cutoff and these metrics are measured on the 0.5 threshold. Then a couple of names that you need to remember is precision. So out of the positives that I predict, predicted actives, how many are actually true positives? How many are real positives, right? So it's the true positive versus all the positives that are predicted. On the other hand, I have recall, which is of all the actives I have in my data set, how many I am able to recall, to get, to remember, yeah? So it's the true positives over the true positives plus the false negatives over the whole real actives that I have, yeah? So these two measures, you can have a model that has a good precision and recall, but at some point, you will have to either go for more precision or more recall, because no model is perfect. So either a model will start to be more precise, so really only make positive what is true positive, or it will have more recall, not miss any potential positives, yeah? So these measures allow us to see how good a model is performing. They depend on the threshold. For example, on a very restrictive threshold, we have a lot of precision. Yes, we are sure that the positive we have are positive, but we are missing a lot of actives. If we have a low threshold, we have a higher recall, so we get a lot of positives, but we will also be getting false positives. Yes, so we will be getting negatives that are actually not true positives. So this is useful, but the problem with this is that you need to define a threshold. So it really depends on the threshold that the authors defined, and the metric can change. So we would ideally like a more general measure that is not dependent on the threshold. Enter area under the ROC curve. I'm sure many of you are familiar with this. So the area under the ROC curve summarizes in a single metric the performance of the model. It uses what we call true positive rate and false positive rate at all these thresholds, 0.1, 0.2, 0.3, okay? You don't need to remember all of it as long as you remember the concept, but just for the sake of it, the true positive rate, it's the sensitivity or recall. The false positive rate is focused on this quarter here of the confusion matrix, and we call it 1 minus the true negative rate, or 1 minus specificity, okay? A lot of concepts. I'll leave the slides there for you to look through. The only thing you need to remember is that when we plot areas under the curve, what if we have a perfect model? Basically, what we have is that our true positive rate, so the number of positives that we are getting is perfect, is high, and our false positive rate is low, is not going up, right? So if we have a model that has an area under the ROC curve of 1, so the area under the curve is all the graph, that's a perfect model. If the area under the curve is 0.5, is only half, so the curve looks something like this, means the model is random. It's actually not being able to predict anything. What we typically have, more real case scenario, is an area under the ROC curve between 0.7, 0.9. So what you want is areas under the curve that go as high up as possible first before going to the right. That is what you need to remember, okay? So this is typically the best measure of performance, the quickest way to assess whether an area under the curve, whether a performance of a classifier is good or not. Areas under the curve, closer to 1, better. Then, for regressors are a bit more directly easy to interpret, right? Because we predict the actual experimental value. It can be an IC50, a percentage of inhibition, whatever it is. So we have our real values and our predicted values. And basically what we want to see is that the real value and the predicted value are the same, right? If it was a perfect model, the real versus predicted values would be the exact same number. Of course, that is not the case. So instead of being perfect, we see how our values deviate a bit, from the actual perfection, right? From the real between predicted is very different. And we have ways to measure this. We won't go much into detail. These are mathematical formulas, but very basically, what we want to measure is the difference between the real versus the predicted value, yeah? The more different they are, the worse the model it is. The closer they are, the better the model is, okay? You can have the mean absolute error or the mean square error. So the smaller the difference is, the better. And then you can have R square, which is the square of R, which is a correlation metric. The closer to 1, the better. That's all you need to remember at the moment. If you're more into mathematics and so on, you can, in case you don't know much about this, you can just go online and look for more information, okay? So today, just this introduction on classification and regression and how we can actually look for, understand how good a model is before I actually use it, okay? So, too long didn't read or too long didn't listen. Classification and regression models, they are useful for drug discovery, very useful, both of them. Chemical representations, aka featurizers, can enhance the performance of models. So by using different featurizations, we may capture different kinds of information. Areas under the curve, precision, and recall are performance metrics for classifiers. Mean absolute errors, R squares, are common performances for regressors. And we must always be critic of the models that we use. Which is the data that has been fed into them? Which are the features that are being used? How was this model validated? Was it experimentally validated? Okay, so now the rest of the course is going to be focusing on to how we can actually use these models and how we can quickly identify the information about the models that is relevant to us. So we are going to go into a more real life settings. There is a lot of unclean data sets out there, as we saw yesterday. They can come from Campbell, from PubMed, from others. There is a lot of work that needs to get into cleaning these data sets for machine learning. And also there is some, it needs to be done very carefully, and there is data sets that are not open and so on and so forth. And to train a model, then once you have the data, you need more expertise on artificial intelligence and machine learning. You need to be proficient in a programming language, typically Python. And so all this is challenging. Luckily for all of us, there is a lot of models that are published monthly. Ersilia publishes models. Many research groups focus on machine learning models for drug discovery, and those could be readily applied and used in your projects. So this is what we are going to focus on today, okay? An applied example. So I'm going to explain now this activity that we are going to do. Is there any important question in the chat to answer at the moment? Or we are good to go?
So Bryce was just asking, what are the factors that go into making the decision for your threshold for the classification models when essentially, I would say, you know, when do you want to prioritize precision or when might you want to prioritize recall?
Yeah. So again, the threshold, the first one, which is on whether a molecule is active or inactive, depending on your experimental data, you do that depending on your knowledge, the experimentalist knowledge, the drug discovery cascade point you are in. On the models, you either just rank molecules and select the top 10 molecules. You may want to be very permissive because you want to find new actives and you don't want to lose them. You don't want to just, get a few actives, but you are in an initial stage of the cascade. In this case, you would choose recall over precision. If you are in a advanced stage where, for example, you want to be sure that your molecules are not toxic, you may want to optimize precision. It really depends on your context. There is no one real answer. There is no perfect threshold. There is not good or bad threshold. It's more about your needs at the moment, the kind of assays that you can do, the kind of molecules that you're looking for, okay? So yeah, so it really depends. And you will see now how authors define different thresholds depending on what they are going to use. So today's exercise is an introduction for tomorrow, and it's very important that we all follow along. So I hope we don't lose anyone in these first steps. So please now don't get lost into 10,000 screens and doing different stuff. Just really walk with me through this first exercise, okay? And you can revise everything or play more with it or read the publications afterwards. Okay, so today we are going to use as example to apply these concepts that we just explained. This model published in 2023, which obviously targets Acinetobacter baumannii. As the title says, it's a deep learning for discovering antibiotics for Acinetobacter baumannii. Okay. The publications are also readily available. You don't jump off and go looking for them. They are on the links again, where in the AI2050 online link, you can find their links to highlighted publications, and we have even highlighted the relevant parts that we are discussing here so that you don't get lost. Please don't go now to read the entire paper. Just wait for it and follow along with me, because I'm going to make the task easier if you stay here. So, and to show you how we can quickly scroll through publications and identify whether they are relevant or not, if you have never read a machine learning paper, this can feel intimidating. All these different plots, these dots everywhere, it can feel very intimidating. Well, it is not. Just with the concepts that we've been over in the last 40 minutes, you should be able to really read this and understand the basic idea behind this publication. This is figure 1 on the paper. We'll only stay on figure 1, but you then are free to go and read through the entire publication, right? So this is figure 1 explanation, which basically summarizes the paper, which is machine learning guided discovery of Abaucin. Abaucin, I don't know how to pronounce that in English, sorry. So let's go. First panel, A. It says, actually it's a schema, it's a schematic representation, where it's telling me that using training data, you can basically obtain training data, you can train a model, then predict compounds and find new antibiotics. Great, we know this, right? So let's see the relevant information here. Machine learning allows for rapid exploration of the chemical space, increasing probability of discovering new chemical matter. Great. We screened 7,500 molecules for those that inhibited the growth of A. baumannii and trained a message passing deep neural network on this growth inhibition dataset, perform predictions here on the drug repurposing hub to find structurally new molecules down here. Okay, so what is important from here is that they use a dataset that they have generated. Okay, so they have the experimental capacity. They have screened 7,500 molecules. And they train a model that they validate experimentally, meaning they do not only do, of course, train test splits to see how good their model is, but they demonstrate that this model effectively is able to predict new antibiotics. And we are going to see how, okay? So this is our baseline. In case you go and read the paper, this is also highlighted in the paper that we provide, which says this chemical collection consists of off-patent drugs and synthetic chemicals. So this is important because it tells us that we are in the synthetic chemical space. Yeah, these are not natural products, these are synthetic chemicals. And the drug repurposing hub, obviously it's approved drugs, yes? So the chemical space of our training set and the set that we are predicting overlap, which is good, means that we'll be able to do good predictions. If you come to this model with a very weird new chemical matter from a plant that you isolated, this model may not predict that good. So here we have the first thing that we need to note down, okay? Which kind of data did we train our model on? Well, synthetic libraries. For second panel, B. Growth inhibition of Abaucin, ATCC, so it's a single strain. Now we should go and look whether this strain is drug resistant, not, etc., etc. So gather information about this strain. We know the concentration it was used, and we know they did 2 biological replicates, so good, it's more or less good data. It's a single point assay, and the actives are these bottom here, red ones. Hit cutoff, this is the cutoff of the experimental data, is defined as 1 standard deviation below the mean of the data set. The mean growth here, okay, so let's look at this a bit in detail. We do a single point inhibition at 50 micromolar. The measure is the growth by optical density, okay? If you read the publication, I'm giving you this information, but you will see this mean growth is basically optical density. Remember that if the bacteria grows, yes, so the molecule is not active, the culture gets darker, whereas if it doesn't grow, the culture is lighter. And we use this mean optical density minus standard deviation as a cutoff. So if we have a cutoff that determines actives inactives, we basically have a classifier. Yeah. So this is what this is telling me. And whenever I predict active or inactive, I am truly predicting active or inactive for this particular experimental setup at 50 micromolar. So if you want actives that are predicted to be active at 10 micromolar, maybe this model is not the best, yeah, because this model is going to predict activity at 50 micromolar. So it's important to understand the experimental conditions of the training data. Okay, so I added some information from the paper here, which is 480 molecules are active, whereas 7,000 are inactive. And we'll talk more about this, but obviously this is an imbalanced data set. This is typically what we find in drug discovery, where we have few actives, a lot of inactives. Okay, panel C. We rank order prediction scores of molecules within the drug repurposing hub by our trained model. Great. So now we take our drug repurposing hub, the drug repurposing hub, we use the model and we get scores, prediction scores. Because no one is telling me anything, I assume this is probability of 1, probability of active. And here is where it says molecules with prediction scores of over 0.2 were considered candidates for experimental validation, okay? So they use 0.2 as the cutoff. That is important. We use the drug repurposing hub, which is the same chemical space as the training molecules. The probability of activity at 50 micromolar is set at 0.2. And basically, how good is this model? We are like missing a step here, right? So we have our training set, and here we are already doing predictions. It's in supplementary data, it's not in the main figure. But if you go look through, it says area under the precision recall curve. We haven't seen this today, we'll see tomorrow, but area under the receiver operating characteristic curve, so area under the ROC curve of 0.79. Yes, so that would be pretty good model, okay? So this is what we know. This model seems to be pretty good. They didn't put the ROC curves here. If you look in the paper, you'll find them. So let's finish this figure. Panel D is simply a TSNE plot that is another dimensionality reduction, where it basically tries to plot the predicted set, the training set, and the molecule that we found, which is this yellow dot here. So this is unsupervised ML, it's just clustering molecules. And what they want to prove is that there is kind of similarity, of course, not perfect, but it's not like our predicting set and training data set are very far apart, are very different, okay? So this is basically what the authors are telling us in this panel. And then finally, below here, we are not going to dive now deeper into that, but what they are showing is how this molecule, one of these predicted actives above 0.2, is actually able to kill the bacteria, okay? So with that, that is all we need to know for this model to actually be able to use it. Now you ask me, how do we use it? Some models are deployed, some models have graphical user interfaces, some are maintained, some are not, and it becomes very, very difficult to leverage this on real life. So this is where the Ersilia Model Hub becomes a useful resource. There may be others out there. The idea of the Ersilia Model Hub is that many experimental researchers, chemists, biologists, and so on, and don't have to do all this process of obtaining data, processing this data, cleaning it, training the models, testing the models, validating them. This requires a lot of expertise. But if we add what we call this deployment layer, we wrap everything that happens inside, everything that we've gone very briefly over in these above slides, so that you can simply come with your drug and get your output and activity. The hub contains, I would say, 180 models at the moment. It will grow, it will continue to grow. And how you can use it, it's very easy. So, sorry, if you want to browse the models that we have, there is this link here. This is also in the Gitbook link. You have at the bottom of the page resources, so links are there. But basically, how you can interact with our hub is you can browse, you can see which models we have. If we don't have models that you want to use and you know good publications or good data sets, you can come to us, we'll include them for you. But you need to point us to the publication or the data set. If you are Python proficient, we encourage you to use a very simple command line interface that you need to install in a Conda environment. So if you know what I'm talking about, you can go ahead and do that. A select number of models is being now incorporated in an online deployment platform, very easy to use. Not all the models will live there, but from now until end of the year, we will do a selection of about 100 models that will remain there for everyone to use. Okay, so now there is only a few of them, the ones that we selected for this course, so that you can try the platform out. It's still under development. This is gonna be finished or completed by the end of the year. We are also developing an easy-to-use interface with the help of large language models. These are work in progress, also not deployed. You will hear more about it when it is. And basically, if you are also yourself building models, you can contribute models to the repository because we always attribute the original author. If you want them to publish a publication, you can mention that your model is deposited in Ersilia. We are a fair repository, so we maintain your model, we make sure it's accessible, we make sure it remains available to the community always, and it's ready to use. So you can save this time for yourself, and we're gonna very happily help you keep this model, maintain it, and you will always be listed out as the author of the model, okay? So that is also an option if you're considering developing your own models. So let's see, in the first one, let's say I am a scientist that I want to do antibiotic drug discovery. I don't have starting points. So the first thing I'm gonna go is browse the hub. As you can see, I typed Acinetobacter in the search bar. Two models popped up, which are the two that we currently have. One of them, this is just a summary. If you click, you will get the link to the publication, etc., etc., etc. But basically, this is the one that we have been discussing. Yeah, the paper that we have been discussing. I just note down the identifier. Models are identified by this number, and then I can go to my online deployment to run predictions. This online deployment, and please don't go there and stay with me 1 second so I show you how it works. It's under this link, hub.ersilia.io. To log in, you need an ID, okay? So you can simply generate an ID. You can keep your ID, so you will have your session always with you. So you can generate the ID with this button, copy it to save it, and basically then log in. You don't need a password, you don't need anything. We don't retain the molecules that you post. We just calculate them, return the results to you, and we don't publish them or anything. Once you are logged in, okay, you have this new evaluation button here. So you click under new evaluation, and it's gonna allow you to select a model. As I said, now there is few models deployed online because this is really for the course, and we will officially release this online deployment at the end of the year, okay? So this is really a test. It may take time to get the results because it will gonna be, I don't know how many, maybe 200 people submitting a request, so just be patient now. We select our model of interest, EOS 3804, select our input file that now we have already prepared for you. I'm going to show you now, and basically submit your job, okay? So this is how you simply can very easily, very quickly get a prediction for this model. So the activity that we will do now, I invite you all to log into this platform, hub.ersilia.io, download the test data. This test data, again, was sent to you via email, and again, is in the link, in the AI2050 online link. You can try to run predictions for model EOS 3804 and download the data, okay? Then we are going to see what are these predictions and see which are the best candidates we get from these predictions. If you manage to complete everything because you are one of the first to submit your prediction, you can then submit the top 10 candidates as a CSV file via the submission link. We are going to have only 20 minutes for this because it's over 200 of you using the same model. The model may go slow. The job may fail because we don't anticipate such a high volume of model usage at the same time always, right? That wouldn't be the case. So be patient. If you don't manage, don't worry, you can try later on in the day. We are gonna show after 20 minutes, after you have some time to play, how we go about then analyzing this result that you will get now or after the course, okay? So I'm gonna now mute myself, stop sharing, and wait for you to play out with the hub, to just browse the platform, or just to read through the publication. Whatever is more useful to you at this moment is, if you are lost, go to the publications and read them. They are marked with the identifier. So just whatever is more useful to you. We'll come back at 13:20 on time, okay? We're gonna be in the chat to answer any questions you may have about specifically the exercise. Other questions will be answered through the Q&A at the end of the session. Okay, folks. Okay, please come back here. I would really ask again that you stop doing whatever you're doing and come back to the main screen and just look at my screen. I'm gonna share how I am doing the steps, okay? Because I see a few doubts. I hope many of you actually managed to understand the exercise and find it. If you submit things that are not correct to Ersilia, the models will return error. And if you just queued your job, that's the expected behavior, because again, we are 200 of us sending requests to one single model, where we typically expect a few people just sending requests to a few models they are using for their research, not on a daily basis, okay? Another important note is if you want to run large calculations in the future, please don't use this online platform because the limits are capped. It's not going to allow you to run 1 million predictions, okay? So if you need to do this, you need to do this through the local deployment because the cloud is capped at a maximum. So let me share, and we'll continue using this platform. We'll get more familiar with it, so don't worry. Let me share the exercise. How do I do this? Would be okay. I hope you can see this tab where I will simply go to the app, the platform. Okay, this is the course platform again. This is the course platform. If you are lost, please come back here. Here you can find the course contents, and here you can find resources, which include the link to the hub interface to browse the models that we have, the code if you have the code, advanced documentation if you are an advanced user that wants to install this locally, and the publications that we are mentioning because they are not open indeed. So we are on day 2. On day 2, we have this link that says dataset for activity. So this is the one that you should be downloading. It's a CSV file that just contains a list of molecules. Once you have downloaded this and saved this in your computer, you go to the hub interface and says session ID. I said first click on this generate ID button, where it's going to assign you a random ID that you can copy and keep for yourself, okay? And then we log in with this ID. And this is what we get, fresh new start. I'm going to run a new evaluation, okay? I first need to select a model. And then I need to select an input file, okay? And the input file needs to be the one that we provided. So if you do this, and then, wait, I need to actually download the file. Just give me 1 second, because I haven't. Let me download this file. If you do this, select the input file, you're going to see these molecules here. Then you can click on submit the job. It's going to queue, okay? We're going to monitor the model, make sure that it's alive and working for this afternoon if you want to practice. But let's say you submit. Once you submit, I'm not going to do it now because I want to get right through the exercise. After you wait, at some point it's going to say completed, and you'll be able to download the results, okay? So let's go to the results. If I done this and I've waited and the model has worked, let me just now share this. I have my molecules, okay? I've put them in a Drive because I use Drive for Excel, for Google Sheets. I have my molecules in a CSV file, and I have my results in another CSV file. So I'm gonna open them with Google Sheets, which is Excel, which is much easier to use, both my molecules and my results. So let's give it a second to load. So basically now I have Excel files of these molecules, which obviously if you open directly in your system in Excel, that's also perfectly fine. So I want to share this. This is the results, okay? It has a column name, Abaucin inhibition probability, pretty obvious, right? So this is the probability that I'm getting, very low for many molecules. So let's see if we find something interesting. And what I am going to do is I'm going to copy my input so that I have the actual smiles, okay? So I'm going to copy this column and just stack it here. So I'm going to have here the smiles so that I can actually see the smiles. The input and output, if you have not unordered anything, they remain the same order, so you can stack them. If you have reordered something, you can no longer stack them because then you'll assign a prediction to smiles that is not the same one, yeah? So they can be stacked. And what I'm going to do very simply now is filter. So I can filter those and I can say, I want to sort these by values and I want the highest first. Remember that what we are using here is a classification model. This is what is important now. We are using a classification model that gives me the probability of inhibition of Abaucin. So I want molecules that are active, so that are highly probable to inhibit Abaucin. If I recall the publication, okay, so I'm gonna go here. If I recall the publication, I want molecules that which threshold did the authors use? 0.2, okay? Remember the presentation, you can go back to the slides or you can go back to the publication. The authors say, we consider anything above 0.2 to be active. So even this molecule here that has a 0.38 would be considered active, would be tested experimentally by the authors of the model. So what I see in my 100 SMILES data set is that I have 10 molecules, these 10 molecules that seem to be active, that are predicted to be active. So if I have the capacity, I will test these 10. Is that clear? I just used a model. I've been informed by the authors of how to read the interpret this model. And then I have ranked my molecules based on predicted activity and selected the top 10, which are the ones that are above the proposed threshold from the authors. Now, is this the only thing we want to know about these molecules? No. We may want to know other characteristics of these molecules. We may want to know if they are toxic. We may want to know if they are difficult to synthesize. So there is a whole number of considerations that we may want to add on top of simply the bioactivity prediction. This is for tomorrow. So tomorrow what we will do is build up on this and see how we can gather more and more information. This is obviously real data, but we have curated this small subset of molecules, okay, so that you can have a good exercise to practice. It's not a real case scenario. These are real molecules. It's just not a real case scenario. The model is real. So let me stop sharing this. Let me go back to the main screen. And let me recap the concept just one last time. Today, we've seen a bit how we can interpret what is the information that we need to interpret a machine learning model, specifically most of it classification models that tell us whether molecules are active or inactive for a particular assay. There is a lot of models out there, and they are not all easy to use or readily available. This is the job of Ersilia, of the organization that I am leading, to collect these models and make them unified in a single place called the Ersilia Model Hub. If you are an advanced user, you can go on and read through the documentation on the Ersilia Model Hub and install it locally, which means you'll be able to run any model that you want locally. This is, again, only for advanced users that are familiar with Conda, that are familiar with Python, that are familiar with Docker. Don't do that if you're not familiar with these technologies. Otherwise, if you want to start using the Ersilia Model Hub, you can start playing around with the deployment platform. This platform has the models free to use. It runs on cloud, okay? So we pay for usage, and the models are scaled for regular usage, meaning if you wake up one day and want to get predictions and you click on a model, you will probably get them in 5 minutes. If you do that on the course when there is 200 people submitting requests to the same model, it will not work, okay? Because we are just really overloading our system. Don't worry about it. You can play with it later in the afternoon. You can maybe try out other models that are already available in the platform. This online platform will be released at the end of the year, okay? At the end of the year, we'll have many more models. Now we are just testing it out and putting the models we are using for the course so we can get feedback from all of you. It's very simple. You input smiles and you get a result that you can then concatenate. We'll work more on this tomorrow. All the models available at Ersilia are either models that we have developed or models that are already published in the literature, in which case you will find the original publication and the author attribution. So these are real models that can be used for real work, for your own research projects. You can mention in publications if you use these models. And if you are developing your own models and want to use the hub as the deployment platform so that you meet all the FAIR requirements for publication of software and machine learning models, which are now required by most journals, you can contact us and we'll guide you through how to use our platform. Our platform is open source, meaning all the code is available, is open access, meaning it can be used without any license. The only thing we require is attribution. If you use our platform, please cite us if you publish the work, okay? If you want to run large calculations, large meaning on the scale of thousands or millions, you need to become either advanced users where you can run your calculations locally. And if it's for a very well-defined research project where you have a need, a clear need, you can contact us and we may see whether we can allocate internal resources to run these large calculations, okay? Other than that, the system is not gonna let you post 1 million calculations, yeah, because it's limited. So I hope this was useful. Don't worry if the processing failed. It is expected that the platform may not hold all the requests at the same time. If you try in the afternoon, if you try other models, I'm sure it will work nicely. And to wrap up, and please go through the resources we share on the AI2050 online workshop link on the platform and take some time to go through the slides again. The video will be updated this evening. You can read the publication again that I presented. You can scroll through the hub and please click on this evaluation form and fill it in. If you did not fill in yesterday's evaluation form, you are still on time. Please do that for yesterday and for today, as this is, and let me make this clear again, a requisite for obtaining the certificate of the course, okay? They are very simple questions. It shouldn't take time to answer. Okay, all right. Then Nicola, any final remarks for the session?
Thank you as always, Gemma, for such a clear, well-delivered session. Thank you so much. You're getting lots of kudos in the chat. So big round of applause for Gemma. Thank you so much. Everyone else, we've been collecting your questions and we're going to apply our minds to answering them later today. All the materials, including the publications, PDF versions of the publications, are accessible on that material for the course link. So if you go there and you just scroll down, you'll see everything that you need. But if you're still struggling, feel free to reach out to me via email. Guys, we're going to see you back here, same time tomorrow. Remember that you need to register for each webinar. So you'll need to register for tomorrow's webinar and for the last day's webinar as well. So each day you've got to register. Okay, so thank you so much. I see some hands are raised. We are at time. Feel free to pop your questions in the chat or email them to me after the session. Thank you so much, everyone. Thanks, Gemma. Bye.
Thank you, everyone.